Yo creo que podemos comenzar y así no retrasamos más el inicio de esta sesión, la sesión 317 del Ateneo de la EINA. Mi nombre es José Antonio Yagüe, soy el director de la escuela que organiza este Ateneo y lo organiza en colaboración muy cercana con el I3A y con la Cátedra Sanca de Desarrollo Tecnológico, que están representadas por Pablo Laguna, que también está presente en esta sesión y que será quien cierre el acto del Ateneo. Muchas gracias a todos por asistir. Me estoy permitiendo hacer esta introducción en español porque así lo hemos hablado con nuestro invitado, que puede entendernos bien, aunque la sesión va a ser en inglés, como ya sabéis. Además de agradecer al I3A y a la Cátedra Sanca, pues por supuesto tenemos que agradecer muy sinceramente la participación de nuestro invitado hoy, Shahzada Ahmad. Bueno, no sé si habré sido muy correcto con el apellido, probablemente no, a quien agradecemos mucho que se conecte a este Ateneo, en este caso desde el País Vasco, donde ahora mismo está. Y por supuesto a Manuel Doblaré, nuestro compañero, que va a ser quien haga la presentación de nuestro invitado hoy, que va a hablar de un tema muy interesante, la democratización de las energías renovables. Es un tema que seguro que tiene muchos matices y es un campo de investigación y de aplicación tremendamente interesante. Bueno, sin más, agradeciendo de nuevo la presencia de todos vosotros, solo quiero indicar unos aspectos prácticos antes de comenzar. Los que estéis conectados por Zoom podéis seguir la sesión perfectamente y podéis hacer preguntas en la parte de abajo, en la parte de preguntas y respuestas. Por favor, no utilicéis el chat, utilizad la parte de preguntas y respuestas. Esas preguntas quedarán escritas y finalmente será Manolo quien se las transmita a nuestro invitado de hoy. También se está retransmitiendo esta sesión por YouTube, por el canal de YouTube de la escuela, y también se puede utilizar ese canal para transmitir preguntas. Y sin más, sí, agradeciendo de nuevo la presencia de todos vosotros, Manolo, te cedo la palabra.
Gracias, José Antonio. Buenas tardes a todos. Pues para mí es un placer volver a estar aquí en el Ateneo una vez más y en particular para actuar como moderador de esta sesión de hoy que va a impartir el profesor Shahzada Ahmad. Shahzada es, bueno, en primer lugar un buen amigo, así que lo que diré estará de alguna manera trufado por esta amistad que nos une. Yo conocí a Shahzada en el año 2011. A finales de 2011, cuando comencé mi andadura como director científico de la empresa Bengoa Research, donde se planteó la contratación de investigadores de todo el mundo en los ámbitos, obviamente, de trabajo de Abengoa, y tuve la ocasión, me llegó casualmente un currículum de un señor que obviamente yo no conocía, de la India, pero que tenía un currículum ya por aquel entonces formidable, y después de la entrevista pertinente decidimos contratarlo y en Abengoa Research estuvo conmigo pues los 5 años que duró la aventura, siendo director del grupo de investigación en energía fotovoltaica en Abengoa Research. Shahzada es doctor en materiales, pero luego ha tenido una dilatada experiencia en distintos países. Hizo una estancia postdoctoral en Max Planck. A continuación se trasladó a EPFL en Lausanne, en Suiza, a trabajar con la persona, con el profesor Michael Gratzel, que es, pues sin ninguna duda, la persona más reconocida en el ámbito mundial en energía fotovoltaica y uno de los investigadores más reputados pues en el mundo. De hecho, tuve la ocasión en el reciente lista que salió del 2% de investigadores más reconocidos en el mundo, aparecía él nada más y nada menos que en primer lugar de todo el mundo, Michael Gretzer. A continuación, como digo, se trasladó a Sevilla a trabajar con nosotros en Abengoa Research y posteriormente allí mismo en Sevilla consiguió una Consolidator Grant de la Unión Europea, la primera ERC que se concedía en España a un investigador en el interior de una empresa, es decir, no trabajando en un centro de investigación público o universidad. Lo que demuestra una vez más la categoría del investigador que tenemos hoy delante. Cuando Abengoa decidió cerrar su empresa de investigación, Shahzada buscó obviamente nuevos lugares y finalmente aterrizó en el Centro de Materiales Funcionales del País Vasco, donde actualmente está como profesor investigador de Ikerbasque. Es una persona que, a pesar de su edad, ya por lo que he dicho, creo que es evidente su categoría y su trayectoria científica, pero que además ha estado reconocida no solo ya por los lugares en los que ha trabajado, sino también por múltiples reconocimientos. Shahzada es, bueno, pues aparte de la concesión de esta ERC que ya he comentado, es fellow de la Academia de Europa de Jóvenes Investigadores, algo que es una distinción realmente importante. También fue elegido miembro de los científicos distinguidos del World Economic Forum jóvenes, que hay 40 nada más en todo el mundo. También recibió el diploma de honor de la Academia de Ingeniería, de la Real Academia de Ingeniería de España. También ha recibido un premio de la Universidad Guangzhou en China. Es editor jefe de una revista de gran prestigio y miembro del comité editorial de varias otras. Y además de todo ello, y de ser una gran persona, además de ello, pues ha trabajado o está trabajando en una serie de temas de enorme importancia. Hoy vamos a tener ocasión de ver algunos de ellos. Él es especialista en materiales y nanomateriales, pero su dedicación fundamentalmente ha estado dirigida a el tratamiento de transferencia de electrones, en definitiva, a el efecto fotoeléctrico y, en definitiva, a el trabajo en distintas aplicaciones de la energía fotovoltaica. Últimamente también está muy interesado en el ámbito de las baterías, pero hoy nos va a ilustrar con parte de su investigación y de su visión en lo que es, como creo que todos sabemos, probablemente uno de los vectores más importantes de las energías del futuro, como es la energía fotovoltaica. Es para este Ateneo y para mí en particular un verdadero placer y un honor tener la ocasión de tener a Shahzada entre nosotros y que nos imparta esta sesión. Shahzada, the floor is yours, cuando quieras.
Thank you very much, Manolo, for such a flattering biography, and Jose Antonio for welcoming me. It's a great pleasure again to be at University of Zaragoza platform, and thank you again for inviting me to give a talk in this Ateneo series, from Faculty of Engineering. I'm simply delighted to accept it, and it's my great honor to be here. So today I will give you a flavor of research which I am doing, and I think renewable energy is particularly interesting and required for our planet. So I will tell you how photovoltaics can be helpful for our planet and what type of research or flavor I'm giving it. But before begin with, let me begin with a famous Chinese proverb. Let me begin with a famous Chinese proverb, and it suits you very well. If you are looking for a 6-month or year, plant crops, wheat, barley, rice. If you are looking for a decade, plant trees. But if you are looking for a century, educate people and build university like Zaragoza, 1542, since it is in the nation of the service, and it is producing an excellent research and different faculty of engineering and sciences. So the Chinese proverb is very well this one. And ladies and gentlemen, I want you to accompany me through a short voice through time. How do I know you? How I know Manuel Doblaré? Manolo, how do I know University of Zaragoza? So I want you to accompany me to this short voyage through time. 11th April 2011, a person sitting in Zaragoza was preparing for his next lecture at 11 o'clock. And he received a phone call from a tall guy, and he said, I have a new model for research and development, and this model has innovation. Finally, Manolo asked, why I? He said, I, because we have a market. And there is a big valley between research and development and innovation. And yet, in my case, we don't have a problem to going to innovation because we already have a market, we have a will, we have a resources, and we will invest time. However, Manolo was not fully convinced and he was sipping his favorite drink. Don't speculate too much. It was Colacao he drank at 10:30 in the morning. So he was sipping his drink and he said, okay, give me some time to think about it and I will be back to you. But the tall guy was very smart guy. He said, before hanging his phone, he said, look, it is in Civel where you grew up. So finally, Manolo has to give up his and agreed what the tall guy wanted to lead a center, which is research and development and innovation. And then from where I had the great pleasure to know him in the summer of 2011 when I came, and he built a center. He built a center which is unprecedented in Spain. From 2012 to 2016, our labs were working, and this 4 years of working, we were given 2 ERC grant, apart from many awards, national and international, more than 560 patents, more than 325 articles. The institute, which is not currently available, but H index of 46, many technological and breakthrough, which have been directly implemented, and know-how, which has been directly implemented in our know-how to cut down the cost, to increase the efficiency of our system. To cut down the cost, increase the efficiency of our system. If you look at the profile of the type of the research this has been done, it is 21. Most of them is what sector of the engineering, energy and material science and chemistry. Engineering is in the fields of material science. More than 10,000 citations just in the 4 years. The institute has gone. It was not, publication was its not main target, but still it was a wonderful model. Like in America, you have it, the Bell Laboratories. And more than 10,000 citation it has received. One of the articles from my colleague Pedro Rodriguez had been cited more than 1,500 times on power converters. So it has been cited more than 1,500 times in the power converter. So this is the way I met him. And this is the fantastic institute. We built it. Unfortunately, we know it had been subject to many written in Nature and Science magazine about what happened to avant-garde research. We don't want to go back. But I don't know, ladies and gentlemen, any institute which has seen such a trajectory in its early phase. So imagine if it had been 5 years or 10 years, we should have made more breakthrough research for the humanity and currently the situation about the European Green Deal. All our projects were completely aligned with the European Green Deals. Just take me to the next slides. Currently, we all know that we are facing, last year, I think, there was an article early last year, 2020, January, was published. It has more than 11,000 scientists, authors from 153 countries, more than 11,000 authors from 153 countries. And these papers, if you will look at it, it was published last year, you say every 10 years, the population of our Earth increases by 15%. CO2 emission, which is going to be 17–18% every decade, it increase, and temperature rising has also seen a jump of increase in the last 10 years. And this, apart from the Paris Agreement, COP21 of capping the CO2 450 ppm, we have already surpasses the Paris Agreement of 450 ppm. Humanity, our population is rising and our comfort level is rising. So this leads to the more CO2 emission by heating and cooling in different parts of the world. And then different type of scenarios is going to be increased in the surface temperature range. And just for your knowledge, I will let you to show a picture on my left-hand side. This picture is across the globe in the month of August 2020, across the globe in the month of August 2020. So the first picture is from San Francisco. It was a forest fire. We already have, most of us read it. The second, we saw the glacier is melting farther than expected. The glacier is melting farther than expected. The third picture is from Southeast Asia, where in August there was a flood. And the fourth one is from Africa. There was a drought. So in the same month of August, different parts of the world are facing different scenarios. And this is based off energy-based catastrophe, is eating away the fabric of our society because most of the people are displaced. They don't have a food to eat and places to live it. So this is the one catastrophe that's happening, and we need to address this solution. apart from the current situations we are all going through, pandemia. And so it's stupid to make the same mistake twice. So it's not like tomorrow we are suffering from infectious disease. Tomorrow we will suffer from climate change. So the World Economic Forum, it launches a great reset button. I think you all will agree with me that there's no better place in our society to learn about the major trend than the World Economic Forum, where entrepreneur, philanthropist, and manager burns their night and policymaker look for the future. So the president of the World Economic Forum has launched a great reset button to learn from our mistakes. Say business as usual is not acceptable. We must change the way we live, how we do business, and respect value. If temperature will keep rising and nature will keep disappearing, we will see more natural disaster and the collapse of our ecosystem. So we must take actions. And so vaccine today is equally important as the solving the energy problems. And our mindset is that we care how much we earn. We don't care how much we burn CO2. So this is also need to be taken into consideration, how much an individual is burning his CO2 emission by his travel and his lifestyle. So today, if you will go to the early, if you look for this early, so after leaving Microsoft, so Bill Gates was a very prominent voice of health and energy. And also for infectious disease and energy, he was talking to the light, and he was proven to be right. We have witnessed, and we are witnessing the phase we all are going through. And still Bill Gates is focusing more on infectious disease and energy, and he need a more mega type of projects on the energy sectors, need a more type of mega projects on the energy like this. If you're more interested, I will direct you to read my agenda, Time to Time I write blogs for the World Economic Forums. So this we have written about perovskite solar cell, which I will come later on that one. But you can read about the new solar technology, which can be printed on web, and how perovskite is going, is a potentially attractive material for photovoltaics. We can also woven into fabrics like this one. You can see we have a 3 layer like in perovskite. It can be go into the cables, and the cable can be then woven into fabrics, so it can be used to build the houses. Shell, which is a very big petrochemical company. You all are familiar with the Shell. Last year, Shell committed a sky scenario. And last year, Shell has prepared a strategy. And this strategy is based on the sky scenario we have it. So Europe, we know that by 2050, we are going to be carbon neutral. Some of the smaller countries are even going to be carbon neutral before than that. By 2035, some small countries have also committed they will be carbon neutral. But how this transition will take place? And if you look at this graph, today we are here. In 2015, we signed the Paris Agreement. Let me take the highlighter. Laser point. Okay. In 2050, we signed the Paris Agreement. And we are increasing the consumption of our photovoltaics, and photovoltaics will be increased, and more than 5,000 gigawatt by 2035 we will be installed. Some country will be by 2040 will be the first one to reach, as I told you, some European country will be even by 2035 they will be carbon neutral. Even the future flight, intercontinental flight, will run on hydrogen. India will lead the solar PV by 2045. CO2 emission will be down, and by 2055, PV will be the main source of energy. Today, it is the fossil fuels, it's oil, but by 2055, the PV will be the main source of energy. The future truck will be run by also hydrogen, and wind, which is a very good also source of energy, will be major source of energy. And by 2070, we will be more carbon neutral. We will go in the negative. Our environment will be much better. We will go in a more carbon neutral environment. Even we will be producing to that one with taxes. So this is the sky scenario. I will come on later on how this will happen in case of photovoltaics. And this is a European Union roadmap for renewable energy transition. And European Unions as a roadmap, they have built it, materials for renewable energy. They have classified in 5 sectors, the photovoltaics, but batteries for electric vehicle, fuel cell, hydrogen generation by electrolysis, and energy efficiency. Photovoltaics is a main contender to bring for carbon-free neutral energy. also which is silicon, BIPV, because in Europe more than 30% of our land is occupied by buildings, so BIPV, CSP, of course, which Spain was one of the leader, wind power in Northern Europe, Denmark, and Ireland, UK will be versatile. Batteries for our electric vehicle energy storage. We want our cars to drive 500 kilometers. Batteries for stationary applications, because battery, we are using more and more electric gadgets, and we need battery for that one. Batteries beyond lithium. Currently, most of the batteries we are using is based on a lithium iron phosphate. And this is not, again, sufficient to power, to feed all the humanity we need it. So we need a new type of batteries, redox flow batteries, zinc batteries, magnesium batteries, polymer-based battery, super caps you all use in your cell phone as a flash, because super caps give you instant power. So in the future, the car, the energy generated from the car is not sufficient to start the car. So you need to start the car with the help of a supercapacitor, and then they will run on a battery. So supercapacitor. Hydrogen for mobility hydrogen is a new vector and leading the European Green Deal. And I think Zaragoza is leading in Spain for hydrogen generation and hydrogen thing consortium. So different type of fuel cells, high temperature, low temperature, hydrogen storage tank with metal organic framework or COF, and onboard hydrogen generation, waterless. Again, we need chemical energy storage and chemical converters, CCU, hydrogen generation by electrolysis, so water splitting with help of electrolyzer, electricity generation from hydrogen, carbon capture and purification, catalytic conversion of CO2 into fuels and chemicals. And the last one is also very important, is energy efficiency, because building requires heating and cooling. So building insulation in colder countries and in warmer countries is a very much required new type of polymers, new type of materials. Thermal energy storage, we were doing it very well in Abengoa. Lighting and glazing, I think lighting and glazing, we are taking the lead, is very good. We have a different organic light emitting diode, which is currently we have a light emitting diode. In future, we will have organic light emitting diode, so it will be more efficient, it will consume less power. And lightweight transport. So this is the European Union road map for materials for energy. The one which is highlighted, you can see, is my area, and I like to work on it because I was always fascinated with the electron transfer reaction. An electron transfer, either it is in the photovoltaic, either is for the battery or the CO2 conversion. So we always study electron transfer reaction with a different type of material. If you look, if you look at this map, how this energy generation by 2050 will take place. So here I have zoomed Europe, and especially in Spain, you will see there's an article published here. So by 2050, Spain will be leading the PV, and 90%, you will see here, this is going to widen and widen, and by 2050 it will be more widened. So Europe, Spain, 90% of its energy will come from photovoltaic. A very small portion will come from hydro. Of course, in north of Spain, there will be, in like Vasca, there will be from some wind, but it's very small. While in the case of UK and Denmark is fully wind dependent, and UK and Ireland will be 50-50 in the wind, offshore and onshore wind. The Spain needs photovoltaic, and it's going to be happen. We are not far that you will see all the rooftop in Spain will be occupied by silicon solar, with the solar cells. I don't know, sorry for my word, it will be silicon or somebody will come there and give a competition. So you can see that Spain and Italy, these two countries will be fully going to be on solar by 2050. Different, because we don't have very heavily on wind and oil converters here, while Germany will be also have onshore wind and offshore wind. PV is already more installed currently than in Spain. In Germany, they are doing photovoltaic farming than plants farming. So this is what is happening here. If you look at the cost of silicon module in Europe is down by 90% between 2009 and 2019. So in just a decade, the silicon photovoltaic cost has been down by 90% module cost. Prediction is difficult. It is difficult to predict, especially about the future. And this was the word from the Niels Bohr, a famous physicist, Niels Bohr. And then I will remind you, this is the famous word from the last German empire, William, last German empire, say, I believe in the horse, and the automobile is a temporary appearance. And he was to be proven wrong. and he was to be proven wrong. If you look at here, different technology for generating power, how photovoltaics has come. If you'll say just in 2010, it was a 40 cent. Today, it is less than 4 cent kilowatt hour. American dollar, 4 cent American dollar kilowatt hour, and it is cheaper than burning fossil fuels. So this graph is from International Renewable Energy Agency area, and you can see this is the gray area. You can see is the fossil fuel based cost range, depending upon which part you are. We have to the fossil fuel has to be traveled or not, transported or not. So if you will see silicon, photovoltaic, whatever it's currently 95% market is silicon, is less than 4 cent kilowatt hour in 2019. And it will be go further down. So auction database is a little bit high. The LCO is levelized cost of electricity is a little bit higher, but the auction database is lower because they have to create more jobs, and some country give you more incentives to bring to the technology to there. If you look at the CSP, it is also almost 18 cent kilowatt hour. In Israel is the lowest, is at 25 cent. We haven't go as a world leader in CSP there. In the offshore wind is onshore wind is even lower, it's a little bit higher than photovoltaics, is 0.043. Offshore wind is just double the amounts. So today we all agree. I mean, we always have a perceptions that renewables are running on subsidy. No, it's other way around. Renewables are not running on the subsidiaries. Renewables are not running on the subsidiary. It is other way around. And fossil today, electricity generation is more cheaper from photovoltaics or wind than burning the fossil fuels. We just need more political will. We just need an ideal technology to bring down the cost. For this, we have to look at the future because we need more energy and we need a new strategy. We have to make a new plan for strategies. So main driver is the growing need for a high performance PV technology. Silicon is a fantastic product today and is helping us a lot and to achieve our goal. But we believe that is not sufficient to power our planet and to fulfill the energy demand of the future. So there's a growing demand of new technology which can compare. We have seen in the last 10 years, we have a revolution in cell phone industry. So we need this type of revolution. We need a high efficient and low material usage, this nanostructure type of solar cells, which can low material usage, which will translate into the low cost, which are also flexible and aesthetic benefits. So we can put on the buildings, our building. Leveraging the levelized cost of LCOE should be lower. Currently, the silicon is 25 years lifetime, and unfortunately, most of the emerging technology is not able to compete with that paradigm of 25 years lifetime. But fully in future, it will be going down. Some new technology will be able to show 25 years plus lifetime. For this, we need a new innovation model, including taking technological risk that we can go to the manufacturing and use all our resources to make this material more stable. And then things that this needs a change in paradigm, and we have to think beyond silicon, what is being happened today beyond silicon, which other technologies can compete. And we have to think in a holistic manner, not only for utility scale, because utility scale is 2/3 of the energy. It's not the full energy. We have BIPV, we have Internet of Things. Many of our gadgets need charging and discharging, so we can make them self-powered devices. And then that doesn't require 25 years of lifetime. Minimize the supply chain, because most of the costs also come from the supply chain. Most of the products are being manufactured elsewhere, and then they travel to Europe. So this is the supply chain demand, and this increases the cost. So if they are being manufactured locally, the supply chain will be minimized and cost will be lower. And ideally, it should be 0.20 cent watt per peak, which is currently 30 cent or even 17 cent last year in Dubai for a silicon solar cell auction. And we need to make an action, and for a medium-term plan, associated budget for a clean tech innovation ecosystem, like we have a European Green Deal, we will see, and it's very difficult, the one with the Chinese government, other Asian governments are giving them to their companies. And establishing a framework of cooperation for niche application, which is go beyond technological wall. There's also other type of industries which will be very well looking forward to adopt new technology, like I said, Internet of Things for self-sustainable devices, greenhouses, consumer industries. So these are looking for a new type of a product to be adopted in the market. If we come to the silicon things, if the photovoltaics is not new, it's almost more than 6 decades. The first silicon solar cell was in 1954 at Bell Labs. It was invented. So if we will classify according to the business model H1, H2, and H3 here, so we will say the business today, the silicon is the 95% of the market come from the silicon. It's the first generation solar cell, the silicon here. The second is HCPV, we call highly concentrated photovoltaics. This is a 3-5 type of a semiconductor they will use. The cell is very small, but you need a lot of lenses and engineering to make it. We were working on that one also. The second needs to come in the late 80s is early 80s. It is a thin film solar cell like cadmium telluride here, which is a commercial product from First Solar. There's only one company is making First Solar because it has a special order to make it, and it has a special permission of resources because there's not enough tellurium is available. So First Solar is making cadmium telluride. This is also the cheapest solar cell than silicon, but we cannot produce more. We don't have enough resources. Then there was another thin film is called CIGS, cadmium, indium, gallium cyanide. Indium is a costly material and you have to save them for your display. You all are using it for cell phone display. CIGS solar cells. So if you will replace indium with a zinc, it will be casterite, CZTS. This is what we are also working on that one. And then the third generation, which is in the laboratory still after last 22 years or 2 decades or 3 decades of research, is we call emerging photovoltaic solar cells. The first one was in this category was dye-sensitized solar cells. You can see this is the facade in EPFL, Ecole Polytechnique Federal de Lausanne. Is a facade of window, different color you can see because they have been using different dyes to make it more aesthetically. And then we have organic photovoltaics. This is a very thin, like perovskite, and it is on the file you can see. And this is also currently giving 19% efficiency. Dye-sensitized solar cells is giving 14% efficiency. And the knowledge we gain from dye-sensitized solar cells and organic solar cells, the community has combined together, and all the research community has jumped in, and we have a perovskite solar cells which give you 25.5% efficiency. Unprecedented efficiency it gave it to date is 25% of height dependence. Then there are also other new type of solar cells like quantum dot solar cells. These are also very effective to give 18% to 16% efficiencies. Today, silicon is a very good product, business as usual, and will prolong the gestation period of our adaptation curve. But we need to take the risk, and we need to develop investing in embryonic technology and risk taking, which can revolutionize our PV industry for our to get mature in the market in the coming 5 years or 10 years. The current market, I will see in 2000, you will see the silicon is like photovoltaics was very well less in deployed, and it has increased gradually by 2005, 2010, and 2015, and you can see it's now like a big giant. Last year alone, 580 gigawatt of new solar was installed. 580 gigawatt in 2019 new solar was installed. Most of these solar cells belong to silicon. And silicon also has a 2 category, monocrystalline silicon and multicrystalline silicon. And only a small portion comes from thin film, which is governed by, we'll see, CIGS and cadmium tellurides. If you look at the graphs, you have a small, only 7.5 gigawatt peak come from thin film solar cell, while monocrystalline silicon is almost 40 gigawatt. Monocrystalline give you higher efficiency, more than 25.5% in lab, but this is also costly. Multicrystalline or polycrystalline silicon is less efficient, 17 to 80%, but it's very cheap. But if you look at this graph here, PV production by technology, so now earlier it was only monocrystalline silicon, but now you will see, polycrystalline silicon, but now you will see that monocrystalline silicon is also capturing the more market because people want more efficient solar cells. And thin film, which was very high in 80s, because most of you has used amorphous silicon from Japan, which was on your watches and calculators. So this market is diminishing. And there we have an entry for a big market with other type of a thin film here. If we will break the thin film market, and we will see the lower picture is from the Fraunhofer, which every year is doing, every year come out. So we have most of the thin film market come from cadmium telluride. And then amorphous silicon is only 0.2 gigawatt peak. And then we have a CIGS solar cells, which is 1.6 gigawatt peak. So thin film market is there, and it will evolve in the future. We do that. So this was about solar cells, and then we have another type of, as I commented before, is the HCPV, we call highly concentrated photovoltaic. It's a 3-5 type of a solar cells. The cell is very small, but the engineering system is works very well, and we have developed in Abengoa our own system, our own boxes, BOS systems, because you need to magnify them at 1200 times the lenses to harvest them more energy. And if you magnify them for 1200 times with the lenses, you will get heated, and then you have to make a heat dissipator to dissipate the heats. And this was a build our own technology at Abengoa. Some of our colleagues were developing that. And this technology uses a different type of tandem solar cells like gallium arsenide phosphide, gallium arsenide, and gallium. So to harvest the whole light, the spectrum of the light. And this tandem configuration is a 45% energy. Energy can be harvested. But this is also very costly, and this is for a niche application like in the city or for satellite application. And this is a picture of a castride solar cells. The CIGS is very good product, is very efficient, 22.6% efficiency, but this indium and indium escalate the cost. So if you replace indium with zinc, you have a castride solar cells, which we also work on. I will come on later on in our laboratory. And then this is a soda lime glass. Then you sputtered a molybdenum on top of them. And you have a formulation of copper, zinc, tellurium, and selenide. And you, by chemical bar deposition, you put cadmium sulfide, and then you sputtered zinc oxide or ITO. This is also very, it's not very efficient, but it's very attractive. The efficiency is 12.6%, the maximum, 11%, 10% we also achieve in our laboratory. But this is also very, very solar cell, which is more stable. And this is a cross section of a diagram, which I told you, you will see that the thickness of these solar cells is 3 micron. And just to give you a flavor, the silicon is 300 micron, between 200 and 300 micron. CIGS and CZTS is 2 to 3 micron, and perovskite is nanometer, 300 nanometer to 500 nanometers. So the lower material is minimize the cost. And this is some new business model or some new type of application. In Abengoa also we did it, and many people are also studying about for niche application like greenhouses, because our, as I commented before, population is increasing and we need food. And we need food. And like Netherlands, which is a very small country, but is the maximum number of greenhouses to date, and is the highest producer of tomato in the world and cucumber, even then bigger than America, a small country. Because why? Because they have a greenhouse, and this greenhouse requires less water. You can do pump farming. And this type of solar cells are very suited well, because we have studied systematically and found that different, not only this is self-sustainable, but the plant also grow faster under different light conditions. Like the tomato, under red light is grow 70% faster, while blue light is good for spinach and lettuce. So if a different spectrum, and this is not difficult with the help of dye-sensitized solar cell or organic solar cells or maybe perovskite solar cell to tune the spectrum. Because if you can tune the band gap, we can tune the light. We can tune the light, different colors can be made, like red colors or brown colors can be made, and so the different plant can be do that. It will be self-sustainable greenhouses, self-powered, so you don't need to put a power sources. Although it will be closed, so the less water will be used in this type of greenhouses. So why we work on a perovskite solar cell? So this is the current status from NREL chart of a single junction solar cells is the current status of a highest efficiency. Silicon is not plotted here, but if you look at the silicon, it's almost flat for last 2 decades or 3 decades, almost flat. You will not see any jump in the efficiency there. So this is our Shockley Castle limit, 33.6. Shockley Castle limit here, but and in last 2 decades you can see organic. Sorry, this one is amorphous silicon is also flat. The one which is increasing is the castorized is 12.6 at the top. The brown one is organic photovoltaic. This is also in the, when perovskite come, I think the community get recharge of the organic photovoltaic also. So they jump from 10% to now 19%. So they are also making very good progress. And now fluorine-free solar cells, the 19% efficiency has been published from the Chinese collaborators, many efficient solar cell. And the red you can see is the rocket. The rocket has rise in just a decade from 2009, or let's say 2012 to today, 25.5%. So this is the unprecedented in the history of a photovoltaic. So we have a material which is efficient, but we need to work more harder to make this material more stable, because perovskite is currently not promised to be given 25 years of lifetime. Either we need a new business model for that one, or we want to make the material more smart. So we have a low cost, we have a high efficiency. What is missing is a high stability. And for this, we need to work out to make a new composition of the perovskite and new things which can make it more stable. As I said, in 2016, World Economic Forum, every year they come with a list. Every year in August, we make a list of the top 10 emerging technology. So in 2016, they come with 2D material, which is graphene. Most of you know, autonomous vehicle, blockchain, next generation batteries, and sensors for IoT, open AI system, optogenetics, and perovskite solar cells was one of them in 2016. 4 years back, and they still discuss it there, and they do that. Even last year, I think I will come on photoelectrochemical cells like water splitting, and we have included photoelectrochemical cells and water splitting or CO2 captures in that. So if you will remember, I show you the sky scenario that there will be transition and how this transition will happen. So if you will look at this graph today 32% of the energy come from the fossil fuels and 22% come from natural gas. Today, set a sky scenario, only 0.5% of our energy comes from PV. This will change by 2070, and 32% of our energy will come from solar alone, and 11% will come from nuclear. How this happens, you will see periodically. If you will follow 2025, the pie chart, and the yellow part you will see keep increasing by 20, and the orange part will keep increasing with the time by 2050, by 2075, and 2021. So this will keep increasing because we believe photovoltaic is an ideal way to harvest light, because sun is the best gift to the humanity, and every hour the sun receives more energy than we consume in a whole year. So we just need a technology which can harvest the light at a corporate price. So perovskite solar cell, silicon is a fantastic product. I don't want to compete with silicon. It's a fantastic product. Let it be there. Let it be there. It has shown all the good things it wants to show. So let it be there. And perovskite to go for a thin film market for different type of applications. Currently, if you look at the LCOE is levelized cost of electricity, means fabrication cost is not lowest for silicon, is lowest for cadmium telluride. And perovskite solar cells even will be more competitive than cadmium telluride. So if you will calculate the cost per peak, the cadmium telluride will be, perovskite will be even cheaper than cadmium telluride, and then crystalline silicon if you watt per meter square. So the cost of ownership is currently less than $20 watt per peak, 20 cents watt per peak, as compared to silicon 45 cent dollar watt per peak for cadmium telluride. Silicon is even higher, but nobody tell you the real number. It is another strategy to boost the job, to make this there. Why perovskite, another type of emerging material? Because we use less material uses and low cost processing. Again, I want to repeat here that 200 to 300 micron thickness you need for a silicon solar cell. 2 to 3 micron you need for a thin film solar cell, and 300 to 400 nanometer you need in the case of perovskite solar cell. For organic, it is even lower. Organic solar cells need 50 to 100 nanometer. There is a term called energy payback time in all the photovoltaic industry. I think this graph may be some true or not, because it depends. Energy payback time always depend upon the region of world you are located in. So crystalline silicon, currently some people also argue it is less than a year, but of course the energy payback time will be different in Sverige than in Denmark and Sweden and in other part of the world. So this is just an average sum of the world. So energy payback time of silicon, crystalline silicon is higher, because silicon you need to heat them, you need silicon at 99.999959 purity. And to make them 5.9 purity, you need to heat them at 1200 degrees centigrade to make it more better, to make a semiconductor grade. That's why this escalates the energy payback time. So, and then ribbon silicon, cadmium telluride, OPV, and perovskite solar cell even lower, because you don't need an energy intensive process. You can only heat them at 100 degrees centigrade, and the perovskite precursor can convert into perovskite material. So titanium dioxide, you need to heat them at 400 degrees to convert from inert to rutile. But if you will take another type of yttrium like tin oxide or zinc oxide, You just heat them at 100 degrees centigrade. So we are not energy intensive process. So energy payback time is very low. I have to a little bit fast. I think I'm going very slow. So perovskite is not a new material. It was researched in early 60s, 1959. You will see in 78 the papers coming from the German researchers. You will find this is written in German if you read them. And it was Gustav Rose who discovered perovskite, and he put the name in the honor of his boss Pewarowski. And that's why the term perovskite came. It's a very broad term. Anything which has a AB X-ray and a crystal structure, it's called perovskite here. And these people in 1958, they studied this type of lead perovskite, which we study today. But what they did only absorption. They say, oh, it's a very fantastic material to be studied because its absorption is a very high absorption. If you absorb very high, you can have a very high current, right? You need an absorber to absorb the light. So they just published a very small, some papers, and then they forget it. And then I think early 90s, IBM was working for organic light emitting diode and transistor because it's a very good semiconductor. And they also left it. And I will come on later on. This in 78 also tin based perovskite was studied here. Why perovskite has attracted so much attention? Because if you look at the best semiconductor, it's gallium arsenide with this 3,5 junction based solar cells. The band gap of 1.43, you can get a VOC of 1.1, so the losses is less. Silicon, the losses is also less, a little bit higher. Perovskite has even similar losses as of silicon because the defect tolerance is very, very high. So if you take it, the methyl ammonium lead triiodide, the band gap is 1.57, 1.55. We can harvest 1.15 volt at least. So the losses, radiative recombination, etc., are less. So while the case in cadmium telluride is very high and CIGS is very high, castride is even high. So that's why castride suffer from low voltage into that. So these are some of the losses is very, very less. These are some of the merits which make them a good absorber material for photovoltaic semiconductor material to do that. The good thing about this emerging photovoltaic is that they absorb in the visible part of the spectrum from 400 to 800 nanometers. So this allows you to think about tandem configuration, and silicon absorb in NIR configuration from 900 to 1. So this will also allow you to make a tandem device, a solar cell. So the visible light can be harvested by top cell. The top cell can be perovskite solar cells, or let's say you can also do organic photovoltaic. And the infrared light can be go back to the by silicon solar cells. So in this way, you can boost the efficiency. You know, single junction is here, tandem, you can boost the efficiency further. And currently, 29.5% of silicon perovskite has been reported, and the maximum silicon, in the lab is 25%. So there are companies which are already working very actively on that one. But for me, it also looked like a double-edged sword because currently silicon is 25% lifetime warranty of 25 years lifetime, which we don't have it. So this is a big trade-off right now. I didn't think I will even think about perovskite tandem, because we can also make wide band gap perovskite, low band gap perovskite. So some we can make it 2.1 electron volt, some we can make it 1.5 electron volt of so high band gap and low band gap perovskite. So perovskite tandem is also being studied. This can be a better bet than pure tandem applications here. So we need more energy, and for this we need innovative technology. I told you this is 1954 in Bell Labs, it was invented, the silicon solar cells. And that time the efficiency was 5 to 6%. And a standard size module of 40 into 65 centimeter was giving that time 20 watt. Today, the same size of module give you 320 watt. And currently, last year, I think I told you 600 gigawatt was installed, and we have an efficient solar cell from 20 to 25%. So most of the market coming from silicon, cadmium telluride, a very small portion, CIGS even smaller than 3.5 for this application. By 2050, it will go up. I think we have to install 500 gigawatt of solar, and for this we need more technology to be part of this party. Silicon, cadmium telluride, CIGS, if the cost can be lower, CZTS, castride, perovskite, silicon tandem, organic photovoltaic, dye-sensitized, or the different type of photovoltaics we need to be that one. Today is here, we have deployed, but we need more deployment, and that's to every rooftop will be having silicon installation, photovoltaic installation, so they will earn even money. They can return back to the tariff, so they will earn more money on that one. And also, this is our perovskite. This is a current tested lab. We have already made 5 years back as 10 centimeter by 10 centimeter. 5 years back, we've made it. And then if our Chinese colleague has also made 1 meter by 1 meter. So these are very, very effective technologies to do that in the future. How to make perovskite more stable, how to make them more better is we need to make new compositional engineering so that the stability can be increased and light absorption can be enhanced. There are the stability and there are defects on the surface. So by passivation strategy, we can minimize the defect because there are grain boundaries and defects which allow to recombinations. We need to develop an different also p-type and n-type. I will come later on. Means p-type we call hole and n-type we call electron transport layer or charge selective layer, because the perovskite is sandwiched between p-type and n-type semiconductors. We need to develop them this type of charge selective layers also, which is not reactive and which are more compatible and cost effective. And avoid the use of dopant and additive. Most of the time, the perovskite, the charge selective layer, or also sometimes the perovskite, you can dope them to increase the efficiency and performance, but this dopant diffuse with time, and you have a loss in efficiencies and performance reliability. So avoid the use of dopant and additive in whole transport material or perovskite active material. And perovskite is a semiconductors. So apart from not only for photovoltaics or building needed photovoltaics, they have a very good application, and I think they have shown even better performance in light emission as a light emitting diode or lasing application, radiation. X-ray converter, they can convert X-ray or gamma rays to visible light. So this is also very good. Siemens is working on that one. Quantum devices, they are also ionic motion, so they are also good for neuromorphic devices. So apart from PV, they are semiconductors. Semiconductors have a lot of applications wherever you want it, and the semiconducting power is good here. What my lab is interested in, we develop a new material on that when we characterize them in the devices. So we characterize the basic characterization, and we test them in the devices, for working devices. If it's not working, we take help of our friend who are expert in theory and simulation to get a feedback and to redesign the material so that by tuning the band gap, by tuning the material properties, etc. So rational designing and crafting of material, what we do that, evaluation of electro-optic properties, as I said here, and simulation feedback to renaissance of material. Perovskite, if you look, this is the cartoon scheme showing the perovskite is the active material, and this is a sandwich between a p-type layer and n-type layer. So what we do that, we take commercially by FTO, ITO glasses we call them. We deposit some layers, n-type layer to increase the surface area, or as an n-type layer, TiO2. Now we use SO2, or we can also use PCBM. We deposit a p-type material on top of it, and we finish the devices by a metallic contact, which can be silver or gold of 60 to 80 nanometers. And the thickness of the perovskite is 400, 500 nanometers. So this is the cross-sectional diagram of an active device. You will see that it's exactly mimic the same structure. The cartoon here, this is the SEM, the scanning electron microscopy images. Perovskite is an active material. It absorbs the light and emit electron and hole pair. And then this electron and hole travel to their respective electrode and get collected. And to harvest the maximum light and make more efficient use electron and hole transport material, which is band gap, matching band gap. So there is no recombination and no issue to get the charge collection. So different type of architect you can use. NIP, what we use generally, because this has been shown to be highly efficient of more than 25.5%. You can get rid of TiO2 and what planar also by using SO2, which we use. And we can also make inverted planar. So you start from p-type layer, then perovskite, and then HTF is a whole transport material. Currently, the stability of is the main issue we are trying to overcome with the different strategies, different direction of research we can work it. The most of the current earlier used perovskite, which I talk about, have been based on 3-dimensional. So now we know that 3-dimensional perovskite is maybe not an ideal candidate. So people are also working on a bilayer type of structure, 2-dimensional and 3-dimensional bilayer, layer and 3-dimensional perovskite, passivated perovskite. So the stability can be increased. I think many good papers have been published more than 1000 hour 85 degree temperatures gradient. You need to encapsulate materials which can encapsulate the device very well. A new type of P-type material, which is a whole transport material, which is dopant free and more stable than a spiral, because a spiral is most of the people uses UV unstable, and some other strategies to modify the SNO2 or putting a carbon paste on top of them to increase the stability. So in this direction, we do we adopt many procedures in our lab in different direction, like compositional and interface engineering, composition to tune the perovskite composition for increasing the stability and increasing the absorption onset, surface passivation to reduce the defects, fill the grain boundaries, hydrophobic encapsulant, molecular encapsulant. I'm talking about like ionic liquid. Ionic liquid, we know this is they are salt but are liquid at room temperature, and they are very good to increase the stability because the surface tension is very high. And then hydrophobic dopant the same unit. And we also design a whole transporting material with the P-type, which can do that. Just to give you a flavor of the research, why what we do that. So in 2012, when we started working, we were working on methylammonium lead triiodide. You can see the crystal size is so small, and there were more crystals. So the more grain boundaries, the higher the number of grain boundaries, the higher the charge recombination, the breeding ground. After working for so many years, and everybody come with a new composition, you can see, and now the crystal size is bigger. Some people, this is mine, very old work, but now the crystal size are much bigger. Even we have, and other people have shown it. The grain boundary is less, so recombination is that we do solvent engineering, put a solvent drop in between to increase the crystal size, and you can see just a representative graph that the efficiency and how has increased it. If you will, before working on a methylammonium. And so methylammonium, you can see onset here, it's absorbed to 780 nanometer. If you put a formaldinium, because formaldinium has a similar atomic radii, one CH2 group extra in methylammonium is formaldinium, you can see that absorption increases. If it will absorb higher, so it will be giving a higher photocurrent, and the band gap has decreased systematically, as we have studied here. The lower band gap, higher absorption will give you a higher value of a current to achieve. And the size of crystal is getting bigger and bigger. This is a pure methylammonium iodide, but if you replace iodine with the bromide, the band gap is higher, but the cells are very transparent. And these transparent cells are very good for building integrated photovoltaic. But they are not very efficient. They will give you 10% or 11% efficiency, but they are more or less semi-transparent. Orange color, you can see them. So this will be good for other applications here. Mostly my labs, and we are interested in doing a solution process or wet chemistry technique, but there's another alternative route also people has adopted, is called thermal evaporation. And this thermal evaporation is most of the people are doing, and they have also shown very good results. And the good thing about thermal evaporation is that you can control the thickness to exactly nanometer, and that will give you high reproducibility. So this is the, if you will see, we talk about bigger grains, and this is good. We hypothesize, but if you do thermally evaporated, the grain are even smaller, with different type of perovskite. This is methylammonium, this is triple cation CSMAFA, this is cesium fluoride, cesium formaldinium. This is tin-based perovskite. We tried many times, but we are unsuccessful till late in terms of higher efficiency and stability. So this is another route most of the people are applying in Spain, also in other places in Singapore. And this is also a very good way to deposit perovskite, because you can control the thickness here to the bit. Now we'll give you some example of our work of interface engineering. And there's this guy who won a Nobel Prize, and they say interface is the device. In any device, interface is the most important. For this, Herbert Kromer won a Nobel Prize, and he coined the term, the interface is the devices. And most of the device parameters depend upon, most of the devices things depend upon the interfaces, how we do that. So if you look at the surface in PV, this is for silicon solar cells. The desirable process are charge separation, charge separated. We want electron and hole to get separated, and extraction of charges of carrier. But undesirable is recombination, because electron and will get recombined. This is a loss, the device get heat up, and contact resistance coming from the different type of materials. This is the case of a silicon. It's also true in case of the perovskite. So you can see this is a perovskite. So you can see the dotted line is undesirable process. We don't want it to happen. And by doing some engineering, interface engineering, you can, or optimizing the material, you can minimize this to some extent, and their performance can be increased. So the dotted line you will follow, it is undesirable. The the electron come back to the perovskite valence band. They get recombined with lost hole, and it's again recombined. The hole also go back to the electrons. These are undesirable process, and we need to stop them and minimize it. So by doing some interfacial engineering, we can achieve that. We can achieve higher VOCs, open circuit voltage. We have to do different type of adopt different type of parameters to do that. This is electrical parameter chart transport layer. The increase of the grain size, minimize the defect. Energy level of charge selective contact, means N type and P type, is very, very important. And the defect traps at the charge selective, we minimize it. We can increase the VOC. This is one example. We did a passivation approach, which is very well organized in silicon solar cell, and this published last year. We use a thazonium iodide basically compound, and we have achieved efficiency a little bit improved, but the voltage was increased to 60-70 millivolts. And a very thin layer we use as a passivation to just passivate the defects, and this shows a higher voltage. We study with the help of a defect spectroscopy more electrical parameters, and you can see the voltage was built-in potential was increased from 750 millivolt to 1180 millivolts. And why? Because the depletion length has increases, so it will travel fast in this. Currently, we're also using another type of passivators elevator. We call it NBS base, which will also has increased a very good voltage from 1.0 to 1.13. So these are our strategy to passivate the defects. This also increase our stability, and our device performs better than that one. So this is a very good, recently we did also last year. We all are very much familiar with 2D material. This is the 2D material we call graphene, but we want to think beyond graphene. And beyond graphene, we use molybdenum sulfide. It's also a 2D material, which also has a band gap. And we put as a special layer because we saw that there was a big gap between the valence band of perovskite and homo of whole transport material. And this valence, there's a big gap is minimizing the energy losses here. You will see that. So we put a thin layer of 2D MOS2, and this has seen a significant jump in the VOC. You can see from 900 it goes to 1110, 1100, almost to a 1050 or 1080 volt. We have seen it. So this is a big boost in this one, and this is you can see a FTO here with a quantum dot. This is the crystal of the perovskite. This is the cross-sectional diagram of devices. We cannot see the MOS2 layer because it was buried under the PTA is a whole transport material. But the devices have very high performance, and they work very well. And the control devices give you only 15%, but these devices work very effectively and give us 18%, 19% efficiency, and much more stable devices we have observed. And to this, we electrical parameters, and we found that the built-in potential was very high in MOS2 devices. We are also studying graphene and many WS2 material, but this material has given a better efficiency and performance than other 2D material. The control devices give you 15% and 14%, while this goes to 19% efficiency with one terminated MOS2 devices. And but this was not the good thing. The good thing was these devices were very, very stable, because 2D material like graphene or MOS2, they are very rigid materials, so they protect the perovskite layer. And why it happens? Because we follow them, and the hydrophobicity of the surface has increased, and the hydrophobicity surface became more hydrophobic, so they were more resistant to the environmental attack from the moisture, and the devices perform very well. You see, this is maximum power point tracking. The red curve is with 2D material, this is without 2D material. So these are the recent results we have achieved last year. Last year also we shifted from methyl ammonium because we know there were some issues to that one, and now we are working on FA-PBI3. Pure FA is not stable, and we make LOI with cesium 0.05%, and we found them is stable. So it's not like a film. We are able to make a powder of that, a pre-synthesized powder, which is very easy. You just need to coat them. This is a perovskite powder. We are able to directly synthesize the powder. The yield is also very high. And believe me, this small bottle is sufficient to make half kilowatt of solar, half kilowatt of a solar small powder, believe me. And also we were able to make it a very low temperature, only 18 degrees centigrade. Normal FePB3 powder is about 150. When we alloy with cesium, we enable them at 80 degrees centigrade, and it works. And pure FA is not a stable powder. You can see that the crystals are not very well oriented. They are featureless, but if you put them with cesium and you heat them in 80-degree centigrade, the pre-synthesized powder, very easy to fabricate now. Anybody can do that. It can be done, make in a kilogram scale. So you have a large size of a crystal. And here if I spin coating, we did it. Let's go to the next one. I will skip a little bit faster now because we are behind the schedule here. This is, we are making it now, studying a bilayer type of a structure, 2D and 3D. And this bilayer structure was, we found that it's increasing their stability to a larger extent. So this is a PAI, this is fluorinated molecules. And we all know that fluorinated molecules have a more high surface tension and they're more better for increasing the stability. And why this is a contact angle has also increased in the 2D molecules, in the 2D molecule with fluorinated, and this becomes more stable perovskite, protect the layers. And we have achieved almost 11% efficiency, sorry, 21% efficiency with the bilayer perovskite, but much higher stability with that one. Pure 2D, we are also studying a pure 2D based perovskite. Layered 2D is called layered perovskite, but they are the quantum confinement is very high because the charges are not coming to the collector, and they're not very highly efficient. So we butylamine, we have doped with lithium, so it works. Increase very good efficiency to 14%. These devices are very, very stable. Where pure layered perovskite structures. So organic chemistry is also very important. You have plenty of things to make a layered structure perovskite, which are more stable, which is now the current demand in the community. And you can choose any organic compound to increase the to make it a layered structure and to make the more perovskite stable. This was published last year with Bengal. And there's another type of research we do is a new type of organic semiconductor, which we talk about as a charge selective layer, P-type material. So the P-type material, most of the commercial people use from is a Spiro, which is commercially available. But we try to also synthesize new type of organic semiconductor. And organic semiconductor is another field of research for the last two decades. Different applications they have it. So for perovskite, there are some rules to use them in or perovskite solar cells. They should be dissolved in orthogonal solvent. This energy level should be matching. They should be transparent and not compete in the light absorption. So different type of organic and inorganic perovskite are there, like copper oxide, copper iodide, nickel oxide. But organic perovskite are better. You can design them by molecular engineering. Polymeric is PTA we buy commercially, and P3HT. This is commercially available. We take them here. So we will. This is the band gap alignment. So before designing any perovskite material, we take care of it and the band gap alignment if it's suitable or not. Otherwise, the charges will not inject. And this is the best performing very old crafts, but FDT, Spiro, and the charcoal type material. These are some examples we developed with a tri-excitation based polymers long back. Whole transport material, because it's worked better than even a Spiro at that point of time. We have a better than that one. The one benzene ring is connected with 3 indole unit, and it was more efficient than a Spiro activity. Currently, we're also studying carbazole based one, and we are changing the position of the sidearm, because the interface is very important. And by changing the position of the sidearm, we can modulate the efficiency and performance of the devices. This new type of carbazole based, this is a pyridine based only. This doesn't work very well, but we put a carbazole group. The film are more uniform. You can see on top of the perovskite, more uniform film. You can see that, and they work very well also to give you 18% of efficiency. Every thin layer goes to 100 nanometer of this type of materials. For building integrated photovoltaic application, we also studying transparent, semi-transparent solar cells. So by purpose, we are making 100 nanometer thick, 100 nanometer thin layer of the perovskite. So you can see through the window here, and this is also giving you 10% or 12% efficiency. We put a dielectric polymer PVDF to make them more stable, and so that binder, they can act as a binder and increase stability. We always learn from Mother Nature, because Mother Nature has teaches us many new things and many clues. And if you take the butterfly and you put under a microscope, it's not like the color is different. They have the same color, but it's the periodical arrangement of the color is different. The same material, but it's a periodical arrangement. That's why they look like a different color. So these type of concepts are very well utilized. We call light management in the silicon solar cell, because by doing so, you increase the band gap of the light. So light can be trapped for a higher duration of time, and you can increase the efficiency. So similar things we studied we modulated titanium dioxide and silica dioxide, because the refractive index of these two materials are very high, very different. TiO2 is 1.4, SiO2 is 1.75. So by doing so, we can also modulate this type of tide management concept, which has been used in silicon. Now we need to emphasize more on this type of things to be more better solar cell fabrication, and this gives also improving our performance. We also use different type of technology, ultra fast spectroscopy, microsecond picosecond to know the charge injection rate, so we can always improve new material, how they're working. We also do a Kelvin probe to know the surface potential and the losses across the things in order to push the performance of our devices and develop new material. So most of the P-type material use a dopant, which are made of lithium. Lithium, we know that is highly combustible and highly hygroscopic. And this is not very stability for this one. So last year, not last year, I think it's when I was going, we developed a new type of dopant, which is based on ionic liquid. It was published in Cell Press in June. We developed it, which is ionic liquid based. Ionic liquid, a very stable material, and we got exactly the same performance, on par performance as of lithium tri-component dopant. So these are also very happy. The good thing that devices are much more stable than that, and we can see the hydrophobicity of the surface is very high. There's another new type of solar cell. I think I told you before. I give you a flavor. It's called castrite, which we work on. And castrite has a buffer layer of cadmium selenide. And cadmium selenide we use by chemical bar deposition. Everybody uses it. We are trying to decrease because the buffer layer. Cadmium is toxic with different type of organic polymers, organic semiconductors like N-type material, PCBM, and we are successfully partially, as was published last year. Castrite, the good thing is that it's not a multivitamin, copper, zinc, tin, and selenium, but it's a very earth-friendly metals, and the efficiency is low, but they're very stable. It's very stable material. Is to give you 12% efficiency. The efficiency is low, but they are because the losses are very high. The voltage deficit is very high in castrite solar cells. So many people in Barcelona are also working. We are collaborating with them also to make it castrites more better and efficient. Yeah. So this was all for a single junction solar cell. If you want to achieve higher efficiency, you have to think about, because currently all these solar cells has a loss in the spectrum. Infrared light is a loss for us only, so you can either harvest this infrared light to some thermoelectric materials. Near infrared region you can use for photonic crystal or making tandem devices, and we only absorb the visible part. So in order to make a more efficient solar cell, either you split the spectrum for a different type of energy devices, or you make a tandem devices so you can increase the efficiency of that one. This is the roadmap for photovoltaic technology where we are today. You know, silicon is close to market maturity for both polycrystalline silicon and monocrystalline silicon. Cadmium telluride is already in the market penetration. CIGS is a fantastic product, but due to the price, it's not able to penetrate the market very well. But perovskite is also, we are at the market entry. We need to solve some problems, and we can go to the market. I think it's the only technology we can go beyond to the Shapley-Kessler limit if you make tandem devices, and is the most efficient third generation emerging technologies. And it is, if some of the problems can be solved, it's going to grow faster, quicker than this one. This is one of the other area which is close to my heart is solar fuel generation or CO2 conversion, because CO2 emission is a big issues. So here what we use, we have used a solar cell of 3,5 gallium arsenide and gallium phosphide 3,5 solar cells. And by use of a suitable catalyst, earth emanating catalyst with copper oxide, you can see the nanowatt of a copper oxide. We can convert CO2 into carbon monoxide. We can again reduce more. It will convert into formic acid, and we can even convert more into methane. So methane is a gas. So it's directly by photolysis, photoelectrochemistry, it can directly convert into energy. So we will be no losses, like in the case of photovoltaic. First you have to convert them, and then it goes to the devices here. So this is the thing we were using photovoltaic and efficient earth emanating cheap catalyst. You can convert them. The light and goes to hydrogen, and hydrogen you can use to feed your car and etc. This is very good. I don't know if the time permit, I can go to the battery thing. Otherwise, I can skip this one. Manolo, do you have 5 minutes?
Well, 5 minutes, okay, but we are a little bit far from.
Okay, so we can just skip the battery for.
Yes, please.
It will be another excuse to come next time to Zaragoza. So I think that future is electric. And there is an electric revolution is going to come, like we have seen in the cell phone industry. So the future is electric, and I have convinced you. I wish I was able to convince you that photovoltaic will be the next source of energy, and how gradually it will take the market share and it will eat it. And it's not like we can just go to the third world countries to be, we don't care about the emissions. So emission, of course, right now India and China are the highest, both are and America also the first one to emit emission. But emission anywhere is a threat to humanity everywhere. At the end, it's a planet is one. So emission anywhere is a threat to humanity everywhere. And we need new technology. We need a carbon neutral technology. In the meantime, we should not emit more CO2 to save our planet. And this was my take-home message, the takeaway with the silicon is a fantastic product, but thin film PV are ready to take off. They're standing on the runway. We just need a more political will and mandate and the will to adopt it. Perovskite is a very blockbuster thin film PV technology, but currently in the lab scale we have it. By doing interfacial engineering is the effective strategy to perform the enhancement. By molecular designing of new organic chemistry, we can develop new type of organic semiconductors to be used in the perovskite material. Testrite is another emerging technology, CZTS. And though I have commented that the efficiency is low, but it's good to watch if somebody can solve the voltage deficit, and it can also goes to 20% because this is a very stable one. And again, the future is electrons. So photoelectrochemistry, you can produce valuable product like CO2, methane, formic acid. You can convert CO2 into methane, and you can directly feed into your traffic. The price competition from silicon, because silicon every day we talk about is the price is going down. So this is a barrier for a new technology to enter the market. And lifetime is low for this sometimes this emerging technology, and we need governmental support and will so that some of the technology can get matured in the future. With this, I like to stop here, and I will be more than happy to take your question. It was my absolute pleasure to give this lecture virtually, though, at Ateneo conferences. Thank you very much.
Thank you very much, Shahzada. And please consider we have given you a virtual applause. So this is something that we usually do when we are present, but unfortunately not possible now. I have some questions here, and we're going to start the colloquium with the audience. The first one comes from Marisa Lopez, and the question is, which composition of perovskites can you evaporate in your lab?
Marisa, I think I was maybe I was not able to convey clearly. What we do wet chemistry, solution process method. We don't do vacuum evaporation. Some people do that, and I think it's also very fantastic. They are reporting very good results. So currently in my lab, we always do solution process or wet chemistry process. So evaporation, we don't do that. So, but I'm familiar that all type of composition, Hank Bonning is a fantastic researcher. He has done a single MAPBI3 or mixed cation, also he has evaporated.
Of course, Marisa, you can ask anything else in our question and answer section. Jose Angel Peña asks you, what about the aging of these materials? And he's talking about the loss of properties a long time, not exactly stability, but about the aging.
Mm-hmm. And yeah, I can read about his next question. What about the use of perovskite in photoelectrolysis? Have you performed? Aging, as I have commented, that perovskite, what we have observed with time, the organic molecule evaporates, and the lead iodide, because we can see from the even colors, the black color became yellow, so it means only lead iodide is there, and then the devices will not work. So we have done it, and we are using different type of some of the flavors I have given you today, doing it to increase the stability, like putting layered perovskite and putting a two-dimensional material, graphene or MOS2 on top of it to make it more stable. Photoelectrolysis, yes, it has been done to produce hydrogen, and perovskite was used as a voltage source, because for splitting water you need 1.23 electron volt, and with the bromide-based perovskite you can easily achieve 1.5 electron volt. So this has been also done for photoelectrolysis to split water and produce hydrogen.
Well, I don't have any more question here, but I have one. Yes, Jorge Sariego. Well, you have it there, right?
Yeah.
Okay, so you can
apart from
just for the rest of the audience, Jorge Sariego asks, apart from PV energy, nuclear energy obtained from fusion reactions can be considered renewable as well because it uses hydrogen, or is it a dirty way?
countries like India and China, they have to live with nuclear for some long time because their consumption is very high. And even we know that our neighbor France is also going to close, but not too soon. So nuclear energy is also an effective way. At least it's less dirty than burning fossil fuels.
Okay, I don't.
But it will be not considered as a renewable. Please, renewable is CO2 emission, and nuclear emit a lot of CO2. So it will be not be considered as a renewable. I hope I answered your question.
You have the one from Manuel Silva. Okay, you have it there. There exists any kind of limit like the law of Moore in transistor integration for perovskites or for solar cells?
Okay, thank you and congratulations, Manuel Silva. I think I'm reading it right for your retirement, and have a very happy retirement life. I saw you last week on Twitter that you get retired. If the same Manuel Silva is asking the question, I don't know. Exactly, all the photovoltaic single junction cell is limited by Shockley-Castle limit, and Shockley-Castle limit for a single junction cell is 33%, because the ideal band gap is 1.1 for electron volt. So all this type of a solar cell is limited by Shockley-Castle limit, which is 33% almost. Though you can overcome, like in the case of 3.5, which is 45% efficient by making a tandem configuration. So in this way, you can absorb a different spectrum of the light, and the efficiency can be pushed. I hope I answered your question, Manuel.
Well, I have a couple of questions before some others come into the list. The first one is very general. I mean, you have presented a very, very promising material as it is perovskites for solar PV applications. It seems that the only con at this moment is stability, but I don't understand why there are some companies investing huge amount of money in this technology, since it seems that it will be part of the future.
Yeah, exactly. Last week also I was organizing a panel. I was in a part of a chair of the panel, and there was one company in America, Hunt Technology, is a very big, from a big family. Like when Goa, it was from a big industrial family. They are investing. And when I go to China, and this guy confirmed me that they have passed IEC. This is the test, IEC 61215 test. So they have passed. Apart from that, when I go to the Chinese, our Chinese colleague also say they have passed it. So these people are betting a lot. Means they don't. I don't know what type of new material they have used, but they claim that they have passed the IEC 61215 test. And if you pass this test, you can go to the market. Okay. Because this is 85% humidity, 85 degree temperature for 1,000 hours. This test is if you can show them 85, you pass this test, and if you pass this test, you can go to the market, because this calculates 25 years lifetime. So some Chinese, yeah, please.
No. So you foresee a perovskite-based solar cells soon in market?
And not soon means, last week Oxford PV, I was the chair of the panel. I asked the Oxford PV, they told me next year. I said, every year you say next year. So I asked him when you are going to the market, he said next year. So I asked him the year, but he said next year. But for me, it looked like another 5 years. But our Chinese colleagues are very optimistic. There are 3-4 companies there also, huge researchers. I think more than 2,000 groups, 2,000 researchers are coming working on perovskite in China. Many Chinese company, and they have optimized the technology which is based on the carbon paste, because the carbon paste they print it 10 micron thin, and the perovskite is infiltrated, so the stability is very high. But that cell also give you low efficiency of 10% or 12% in the module.
Okay, good. And do you foresee first the application in building integrated photovoltaics or in the large-scale solar plants?
The main perovskite will be for PV application, because this is also a dark color, so it will be not go for a BIPV application. For BIPV application, they have to minimize the thickness, but then it will be not efficient, like some example I have shown you. Or maybe OPV and diced solar cell are more suited for BIPV applications.
Okay, this is something that surprised me a little in your presentation, because you presented the SSC as an emerging technology. And well, it is almost 20 years, maybe.
Yeah, 20, but it's not going to mass production. That's why we are very careful with our word. I mean, there are some companies which manufacture for small devices, but mass production is for, like you say, megawatt production or 100 of megawatt production scale.
Okay, I would like to open also a new question that probably will produce some other questions from the audience. You have been working in Germany, in Switzerland,
yes,
in China, in India,
China,
in Spain.
No?
Well, can you tell us what's your opinion about some of the defects of the Spanish R&D system that, in your opinion, could be solved in order to have a more efficient and more and a stronger system?
So this will be politically incorrect because this is live on YouTube and Facebook. So I don't want to go in any controversy because this will be.
Sure. No, but this is a colloquium. I mean, you are in a family. So.
Okay, I'm in a family. Thank you very much for clarifying. So I don't want to comment more, but let me give you an example. I was in Germany in 2009 and 2010. And that time there was a big debate in German parliament that the Max Planck is not getting a Nobel and we are investing. What happened? The Max Planck president at that point of time, I'm just missing the name, and other group, a committee was formed. And this committee traveled across the world. And they bring that time 20 researchers. One of them, the lady won Nobel Prize this year. So in last 10 years, after that travel, they went across to America, other places, they identified people, bring them back and give them the resources they want. And last 5 years, you see, Max Planck got 4 Nobel Prizes, 5 Nobel Prizes. So the manager where the German parliament were discussion, the manager Max Planck, the committee was formed, it went to travel to, the lady was in America, then she was brought in Sweden, then she went back to German university, then became a Max Planck director, and this year she won on the CRISP, you know, that the Nobel Prize. So this is not only case, more than 20 people have been brought to Germany in that period of time, and 5 already won a Nobel Prize. So we need to identify people, and like you said, I know, you said, give them resources, this is what your word,
yep,
and give them the liberty to do what they want.
Yes, I fully agree on that. Okay, is there any other comment, any other question in the audience, please?
If you look at the graph, if you go to the Web of Science and see the perovskite paper, China is a leader today. And it was formed in Europe, you know, perovskite was made in Europe. The first production of paper is from China, then it is America, and then other countries. Unfortunately, in top 10, Spain is also there in spite of our very sluggish funding situation in Spain. Many people are working very hard on that one, many people in here. And most of the means, if you will go on the Web of Science, you will see the percentage is very low of Europe even. Because the Chinese, there are more than 2,000 researchers working, 200, 300 professors.
It's clear. Okay, thank you very much. Is there any other question in the audience, please? No one else? So, well, I'm going to thank you again, Shahzada, for your magnificent intervention. And I think that Pablo, the director of the A3A, is closing the colloquium, the session.
Yes, thank you very much, Manuel, and thank you very much, Shahzada, for your very nice presentation. We have enjoyed a lot. We have learned the tendencies for this very important issue for humanity, I will say. And I am personally far away from the topic, but I really enjoy to see how the situation is, and well, kind of getting optimism to see that the path is quite promising in more than a linear way. So thanks a lot for your intervention. It's a pleasure for the Ateneo to have you here, as has been already said. We usually end this presentation with a small gift, just to remember this presentation. Obviously now we cannot do that personally in this moment, but we compromise to make it arriving at some time in the next days in your mail. So in the meantime, thanks a lot, and I'm sure we can follow up your work in the near future with high interest. Thanks a lot, and muchas gracias a todo el mundo. Muchísimas gracias a Manolo y Shahzada de nuevo en castellano por vuestra presentación, y quedamos emplazados a un próximo Ateneo. Muchas gracias.
Thank you for having me, Pablo. Thank you, Manolo, for arranging it. And I think you all agree with me that future is electric. Either is a battery, either hydrogen or solar cell. The future is electric.
Very good. Thank you very much.
Thank you very much.
Thank you very much.
Bye bye to everyone.
Bye,
hasta luego y hasta un próximo Ateneo a todos. Gracias.
Gracias, Pablo.